we're really
Also,
happy
it's
to
recorded.
we're really happy to have Bohyun Kim here, who is, as I said, an academic sibling of mine. She graduated from UCLA this past year with a PhD under the advice of Andrea Bertozzi. But she's going to tell us today about a positivity preserve. I should say she's now at the University of Utah on a postdoc, and she's going to tell us about a positivity preserving numerical method for a thin liquid film on a vertical fiber. So, Boyan, thank you so much for being here, and take it away.
Yeah, thank you so much for inviting me. I don't know. I've just become a postdoc, and then this early career talk sounds like a very fancy name for me. So I'm really honored to join all of you. So today I'm going to talk about my PhD thesis work. This is joint work with Dr. Hangji Ji from the North Carolina State University, Dr. Andrea Bertozzi, who's from University of California, Los Angeles, UCLA, and some other doctors who are in the math engineering department, who is Albafaza Sadefur and Y Sungtik Ju. And yes, so let's get started. So when a thin annular layer of liquid flows on a narrow vertical cylindrical fiber, such as a hair or a microscale tube, a fascinating physical phenomenon can be observed. The flow become unstable, resulting in droplet formation, irregular traveling waves, and the formation of strings of bead. In particular, traveling bead pattern creates a high curvature region that acts as radial sink, thus enhance vapor diffusion towards the liquid surface. These patterns provide a suitable geometry for designing heat and mass transfer devices along the liquid-gas interfaces. Such application can be found in various fields, including gas absorption, mass and heat exchanger, ultrafine particle capturing, microfluidics, and desalination. The specific application that I focused throughout my PhD was the desalination device. And I was in the California, so it makes sense that we care about like fresh water. So here is a figure illustrating the representative dynamics of a falling film. So this isn't really on a vertical fiber, but this is still, do you guys see my mouse? By any chance?
Yeah.
Okay. Yeah, this isn't really the cylinder. It's on a vertical fiber, but it's still relevant dynamic because this is a fluid falling, a viscous fluid falling. And so it demonstrates how velocity, pressure, and stream function vary in a contour map. And V represents the velocity of the fluid in the horizontal direction, P represents pressure, and phi represents the stream function. So at UCLA, Professor Sungtik Ju and his collaborator has recently developed a new vapor capturing or dehumidifying device based on the concept of fiber coating. In 2019 Science Advance article, they reported that their dehumidifying devices achieve a condensation rate per volume that is twice as high as the current state-of-art devices. Additionally, their device is lightweight, cost-effective, and exhibit remarkable tolerance to high salinity. And can produce high quality diesel water. And if you look at this video, you see the relevant dynamics of a fiber, and this is how the real device look like. This is zoomed. If you can see person on the back, so this is a very big device, but also have a very thin string as well. So on the left-hand side, we can see a simplified setup for the experiment. A programmable syringe is used to pump the liquid into the nozzle, generating flows. The fluid used in the experiment is well-wetting liquid with low surface energy and high viscosity. So it's important that we're considering high viscosity liquid at the moment. On the right-hand side, we can observe the 3 different flow regime, which can be achieved by varying flow rate, fiber radius, and nozzle sizes. Generally speaking, increasing the flow rate results in smaller interbead spacing while keeping the velocity of the beads constant. Increasing the nozzle size leads to larger droplets, spacing, and velocity. Increasing the fiber radius results in smaller interbead spacing. We'll refer to these 3 regimes as a convective regime, Rayleigh-Plateau regime, and isolated droplet regime. The convective regime is observed at the high flow rate, characterized by irregular droplets colliding with each other. the Rayleigh plateau regime is characterized by bead traveling waves propagating at the almost constant rate. And the isolated droplet regime is observed at low flow rate, characterized by small wavy flows followed by the large separated droplet. So if you take a look at the Rayleigh plateau and isolated droplet regime, many people will question that aren't they just same regime but with the different bead spacing. But if you actually see the isolated droplet regime, one can see a smaller wave that is contributed and then the instability is contributed because the big droplets are separated apart very far. So here we see a fiber coating simulation versus experiment rotated by the 90 degrees. And fiber coating has been studied since 1990s, which may lead to question of what further research can be conducted. In short, there is a room for improvement for mathematical theory and numerical simulation. The dynamics of fiber coating can be simulated using software like ANSYS, is noted on the top of the video, which utilize the full Navier-Stokes equation for simulation. For instances, this particular simulation employed a second-order upwind scheme to simulate the 2D axisymmetric Navier-Stokes equation. However, simulating the full Navier-Stokes equation can be computationally expensive. I was also surprised to learn that the license is quite costly. NC's license was around 30K per year. But most importantly, these simulations often do not provide sufficient information about the regime transition and downstream dynamics of the flow, which are most important to consider for designing heat conducting or mass transferring devices. To address this limitation, many reduced order models have been proposed under the assumption that the fluids have moderate Reynolds number. Such approach can provide a valuable insight into the regime transitions and downstream dynamics of the flow while reducing computational complexity and cost. One well-known technique is the lubrication approximation. The lubrication approximation can be applied to a thin viscous fluid. Lubrication approximation can reduce two-dimensional Navier-Stokes equation to the equation on the right with the appropriate scaling. Assuming the low Reynolds number, in other words, or Reynolds number that is O1, and a slender limit. So we're assuming that the film is very thin, so the H is relatively small compared to the length scale, which is given by this direction, U direction. And we're also assuming the flow has a low Reynolds number. So under this assumption, the full Navier-Stokes equation can be simplified into lubrication approximation. Then one can apply proper boundary condition and conservation of mass to get the Reynolds lubrication equation, which is given by this equation.
I have a question.
Yes.
So this is for the incompressible Navier-Stokes, right? So first question, what about 3D Navier-Stokes? The second question, what about the compressible Navier-Stokes?
Compressible. No,
yeah.
I don't think we can apply this. So we assume further is a low Reynolds number, which means the fluid is pretty viscous. So under this assumption, you're able to take the O of epsilon term. That's what we're doing. Basically, we're approximating this asymptotically and only taking O of epsilon term, and then the equation reduced down to the following.
But you mean the compressible Navier-Stokes is not viscous?
So I'm considering non-Newtonian fluid at the moment. So
I see.
Not compressible at the moment.
So but this is for 2D. What about 3D? Can you do 3D?
3D, yes. 3D you can do that too. 3D it'll be compressed down to the 2D equation now. The reason why I consider 2D is because I'm considering axisymmetric Navier-Stokes equation. So that's why I'm considering 2D at the moment. But 3D, certainly you can do it, and a lot of people does it too.
I see. What about the Euler invited? What could go wrong? for the inviscid instead of viscous.
Will it?
Yeah.
Inviscid one, that one you assume the Reynolds number are relatively high.
Yes.
So I don't think you can apply. You can approximate this exact method.
Okay.
So it is really crucial that you consider the low Reynolds number flow, which are viscous flow in this case.
Thank you.
Thank you so much for the question. That was very good question. So Reynolds lubrication equation is an evaluation equation that describes dimensionless film thickness H of xt. The typical boundary conditions for the PDE include the periodic boundary condition and Neumann boundary condition. The mobility function M of H describes the hydrodynamic interaction and between the liquid and solid interface, and can incorporate conditions at the solid liquid interface. For example, one can prescribe no slip boundary condition or a slip boundary condition and porous surface boundary condition, and that'll change the mobility function and how it look like. Dynamic pressure P represents the different type of pressure incorporated in this fluid, and HXX is a linearized surface tension, and by the Gibbs-Thompson law, you can see that the pressure is a pressure difference is gamma kappa. Kappa is a curvature, right? That's why we get surface tension of HXX. Disjoining pressure Z of H and other nonlinear pressure effect can be incorporated in the Z of H. One of the popular one is Z of H, that is negative AH over H cubed, and this incorporates the van der Waals forces and it stabilizes the liquid. But we'll discuss other types of disjoining pressure later on as well. The state-of-the-art model for the fiber coating problem is quite complicated because in addition to the classical lubrication equation, we incorporate many different terms such as cylindrical geometry and advection. The flow is flowing down from top to bottom, so it's only natural for you to include the advection term. So using this wonderful theory, and other mathematicians have developed a model that describes the coating fluid dynamics of a vertical fiber. This is considered the state of our formula, and there are a few notable differences, such as cylindrical flow and then advection, like I said. So the cylindrical flow, this alpha term is incorporating the cylinder geometry by having H over R, where H is the thickness of the flow and R is the fiber radius. So having set that greater than equal to 0, or having that large number would indicate the flow is thicker relative to the fiber radius, and so on. Setting that equal to 0 would consider a flat geometry instead of cylinder. So mobility function, as I described, will be more complicated because now we have to consider the cylindrical interface between liquid and solid. And then phi represent the shape function of the cylinder. Now we consider P as H of second derivative minus Z of H, where H of XX is a linearized curvature and Z of H is a nonlinear pressure term. For example, destabilizing azimuthal curvature term can be incorporated as alpha over eta 1 plus alpha H. All of the constants are positive, and stabilization due to the van der Waals forces can be incorporated as minus A over H cubed. And these has been discussed in classical literature, for example, Dijon et al. So these are well-known type of a nonlinear pressure term that's been considered since 1980s. Yes. So just to add one more thing, this is a 1D equation. So it looks very complicated, but it's still 1D. So that helps a lot. And let me talk about the positivity failure. The previous equation was derived using the lubrication approximation, meaning that we assume that thin liquid is liquid is thin and viscous, but the figure represented here provides an example of traveling droplet. Imagine this droplet is 90-degree rotated, so the one that is flowing from top to bottom will be going to left to right. You will see this droplet traveling to the right-hand side, right where the H represent the film thickness, and then X represent the fiber fluid direction. In the case when the film thickness H is very, very small, numerical methods can cause false negativity. In other words, even if the analytical solution of the PDE is positive everywhere, the solution produced by a naive numerical method can have negative values. This often result and require in significant grid refinement, and one has to decrease the time step, and therefore it adds additional and very expensive computation costs to the simulation. Negativity is also undesirable because it prevents continuation of the simulation. When the equation that we had is actually degenerate fourth order equation, where as H becomes 0, the solution will lose regularity typically. Therefore, that the numerical method will not be able to proceed to calculate from then on. So not only the preserving the positivity is important for having a physically meaningful and accurate solution, but also it's important for simulation to continue.
Can I ask when this happens in Hamilton-Jacobi equations too, which I work on when you break something like that, break monotonicity or positivity, things just blow up. Is that the same thing that happens here? Like you try.
Yes, exactly.
Okay. Cool.
Yeah,
Cool.
basically the fourth derivative drove up, and it's fourth derivative.
Mm,
So
gotcha.
yes, even maybe worse. So that's exactly the intuition that we had. But what's important about it is that if you simulate these in a very, very fine mesh, which will mimic the analytical solution, you actually never see negativity anywhere. And it's not possible to form a negativity because physically, the solution will only, the liquid will only touch the cylinder if the velocity is infinite or 0. So physically it doesn't make sense either. And then here I wanted to outline the agenda for this presentation. There's a lot of background into this because this is a well-developed field. So I will first provide a background to give you insight on how this problem can be approached and discuss relevant recent research, and also talk about positivity or non-negativity preserving numerical method for lubrication type equation. Next, I will present our contribution to the project, which include proving properties of our PDE solution under some smoothness assumption. And additionally, we'll introduce our positivity preserving numerical method known as a bounded entropy method and showcase it through several simulation example. And finally, we'll conclude and then talk about future work. So first, let me introduce a few mathematical properties of a lubrication type equation. Lubrication type equations are degenerate parabolic fourth order partial differential equation. Solution to this equation is smooth as long as it remains positive, but it typically loses regularity as H goes to 0. Since this is a higher order PDE, meaning like third order or higher, we cannot rely on maximum principle to establish positivity of the solution. There are other properties like the solution exhibit a finite time singularity when your n, which is from the mobility is typically of order n, h to the n function. If given n small, you'll see a finite time singularity, but it has been proved that n greater than or 3.5 for large n, interestingly enough, the analytical solution is positive anytime, everywhere. So given that the initial solution is positive, I mean that's important. And regularity of the weak solution and non-negativity has been proven through various papers, and propagation of support of the solution is also discussed because the support of the solution represent the contact line of a thin film, and that contact line behavior has been interest to a lot of engineers and physicists. So the propagation of the support became also interesting topic. Recent positivity preserving numerical methods. So the recent research on positivity preserving numerical method can be summarized in this slide. And we note that the most positivity preserving numerical method for partial differential equations are limited to the first or second order equation. And this limitation usually arises because of the lack of maximum principle, and because once we try to take a higher order spatial derivative, numerical system becomes extremely stiff. Therefore, just dividing by dx many times, just not good. You know, some recent approaches utilize cutoff or Lagrange multiply method, but these methods have limitation in terms of conserving mass and maintaining stability of numerical method. Convex splitting method has been employed to preserve physical quantities such as energy, entropy, and mass. These methods treat the stabilizing term implicitly and destabilizing term explicitly. One recent method I wish to point out was the scalar auxiliary variable method provided by Huang et al. This can be used to solve Canhillier type equation, and it provides the upper and lower bound as well as it's unconditionally stable. So pretty impressive. Our contribution to this project is that first we provide the energy and entropy estimate for the continuous solution, and we propose computationally efficiently numerical method that can maintain the positivity of the film thickness by preserving discrete entropy estimate, and we'll talk about this more in detail at any grid side. We also proved that the model is second order consistent. We compared our numerical method to laboratory experimental data to show the real applicability of our numerical method. And we also suggest an algorithm for efficient implementation, which is to use adaptive time stepping method. The article was recently accepted by the Journal of Computational Physics. Open access available. It'll be available in 5 days, they said. So very recent publication. And the code and the data are also available on my GitHub repository if anyone is interested in running the code or have any questions. So our problem, let's review our problem. Our problem is given by the following equation. So this is fourth order equation because we are taking second derivative of p, and p contains h of second derivative. So this is a fourth order PDE that incorporates advection. Advection can sometimes introduce jump discontinuity or stuff like that. So that despite the parabolicity given by this p fourth derivative, we see that this advection can mess up really things. And yeah, and we prescribe periodic boundary condition because this was the easiest condition, but one can also consider constant flux condition. And then we assume the initial value is positive because otherwise it wouldn't make sense physically as well. And we wouldn't be interested in not physical solution, to be honest. So we refer to the above problem as a P from now on. In general, we'll assume that our mobility function M of H will be a power function of order H, M of H greater than equal to 0, and then our disjoining pressure term Z has a convex and concave term splitting, where Z plus prime is greater than equal to 0, and Z minus prime is negative less than equal to 0. So we're assuming z plus to be convex function and z minus integral of z plus will be convex function and integral of z minus be concave function. So such splitting is not unique, but we're going to assume that it is possible for many cases. So these are not too crazy assumptions so far, but maybe assuming that solution is C4 is a bit crazy. But actually, we don't really need C4. This was so for the sake of, presenting numerical method. The actual condition we need is actually C2 in space and C1 in time. And the condition that written down here is the condition that I mentioned, that M is a power function and then Z and Z minus has a concave convex splitting. So these type of assumption, these two assumptions, we're going to assume it throughout the paper, but I'm just going to write it down multiple times in case people have forgotten it. And I'm going to define this function G prime, which is 1 plus alpha h integral of a to h 1 over mobility function mk dk for some constant a positive. So a doesn't explicitly come out, so it doesn't actually is important. It's actually not important at all. It's not used for any of the proof or the numerical method. It's just here to assure well-definedness. The reason why we sort of assume that equation can be C2 and C1 in time is because throughout a lot of simulation and tested very thoroughly, depending on simulation and then parameter, we saw that the third derivative and the fourth derivative of h was smooth and bounded over time. So that was the reason why we thought it was okay to assume for now. Right. So then given these above property, we can show that our solution H satisfy conservation of mass energy estimate. So the first proof is quite simple. You just integrate and then apply boundary condition and you get conservation of mass. Because this is a periodic boundary condition, you have to have a mass conservation. Second one is entropy estimate, and this you can derive it by taking derivative of g of h, where g of h prime is defined as here. So now you get g prime times h of t, so g prime times h of t, and then you do integration by parts, and you'll be able to get this entropy estimate at the end. So, here is what I wanted to talk about the most, and this is perhaps the most important slide in my talk. The key of proving positivity, or key of constructing a positivity preserving numerical method, is to utilize this function called G, which is entropy. So typically G has property where if you take the double prime of G, it will be like 1 over h and m of h. So it's the negative to power function to the negative power, right? So if you integrate this twice, it's going to be so like 1 over h cubed kind of looking thing, or ln with the negative sign. So bounding g of h will guarantee, bounding g of h from top will guarantee lower bound of h, because it's 1 over h squared, and then if you have a top bound inverted, and then you get a lower bound for h. So that's basic trick for the getting positivity solution. So from proposition 2.1, we got that from the second part that g of h of xt in the later time t is bounded above by the g at the initial time and this quantity. So if we're able to successfully bound these quantity from top, we should be able to recover h, lower bound of h. So that is the idea, really. Does that make sense? Or yeah. Maybe it's a little bit fast. But so this is how that is exactly how our bounded entropy method is designed. So we created our positivity preserving finite difference method called bounded entropy method to preserve discrete equivalent of the entropy estimate. So there is a continuous version of this, and then suppose we can create a discrete equivalent of it. And if we can if we can create a numerical method that preserve discrete equivalent, we should be able to find the recover numerical solution that is non-negative everywhere or positive everywhere. So okay, so the continuous in time finite difference discretization BM is used as follow, where forward and backward difference are noted as forward as in just x without the bar, backward as in with the bar. So this is how you would, and then pi is given by the u second derivative, second order differences, and then z plus and z minus. And mobility is discretized in this particular way, and this particular way is important because this exact value is used to show that our discrete solutions able to preserve discrete equivalent of entropy estimate. So suppose UIT is a solution of BEM at time t and on the ith grid, and suppose we further assume that these regular property that we have assumed true, and then define G prime of H as following, then we are able to show that UIT satisfy the following discrete equivalent statement of conservation of mass and discrete entropy estimate. So really, we have just changed the integral over space to the summation in X. And we are able to show this by first one doing integration, doing summation and then using boundary condition. Second one taking derivative with respect to G. So here's our main theorem. First three assumptions are the same, but we add one more assumption, that our z minus is bounded by some constant. So and given the positive data, then the solution of BEM at time t UIT satisfy the following condition. First, if n, the power of the mobility, is given greater than equal to 2, then there exists delta that depends on delta x, the grid size, but our solution is still guaranteed to be positive. If n is strict than 0, the exponent on the mobility power is strictly greater than 0, then the UIT is uniformly Lipschitz. And this is a posterior assumption that we're making. Suppose that n is greater than 2 and UIT satisfy uniform Lipschitz condition, then we're able to find a posterior lower bound delta that is independent of grid size. So our solution will be guaranteed to be positive. The sketch of the proof goes following. For simplicity, one can take m of h to h to the n, and we solve for g of h explicitly that way. We define g prime of h to be the following. Therefore, one can explicitly solve for g. And entropy estimate says that G of UIT at the later time is bounded by this quantity plus this quantity. The first quantity is bounded because initial data was given to be positive, which guarantees the G at the initial data to be positive. Second one, this is because Z minus, we just got bound, we just assume there is a bound for Z minus. And if you have a finite time for that, then you can bound this quantity. So therefore, this G at the later time t is bounded by some constant. And you solve for G delta explicitly, where delta is the minimum at the U. If you solve for delta, the first term for n equals to 2 is negative ln delta. Second term is delta to the negative power.
This is also delta to the negative power, delta to the negative power. So because this is bounded above, we can recover the fact that delta cannot go to 0. Therefore, our minimum of the numerical solution will not go to 0 and will be positive, therefore. One can use a similar argument, but one can use the uniform Lipschitz assumption to simplify G of UIT term. So basically, uniform Lipschitz will be able to rewrite this minimum as some UI plus the Lipschitz term. So therefore, one is still able to find the constant and then approximate that summation by integral. Therefore, you can get a fixed constant that doesn't depend on delta x. So additional result is that this continuous in time discrete in space BEM method can be applied for the state of R method given by Kester-Matar model and then the Phelan stabilization model by G et al., which are popularly used. We've also proved second order consistency in space. Therefore, yeah, where the local truncation is order 2, basically in space. So until now, I was talking about continuous in time and discrete in space method, but practically you have to, if you wanted to implement this, you have to consider discretizing for the time. So discretizing for the time was specifically taken to this form to guarantee the conservation of numerical flux at each time. And this particular discretization also allows conservation of mass. And one can see that here the pi k plus 1 is discretized this way, where the z plus is discretized implicitly, z minus is discretized explicitly. This is well-known method to guarantee to make numerical method more stable. This is convex concave operating splitting discretization. Yep. Yeah. So we considered the following numerical simulation. We took the equation from Kester-Matar and G et al. And really just substitute. And the example demonstrated a good matching to the laboratory experimental data. Yeah, and this above variable and definition satisfy our theorem, and codes and data are available on GitHub for this one as well. So given a slightly perturbed initial state, if you simulate the equation, you achieve this kind of droplet formation of a thin film. The left one is a Rayleigh plateau regime, and then right one is an isolated droplet regime. If you see this one more time, isolated droplet regime, you see there are multiple droplets moving at a different speed because of the mass of the droplet. So if the mass of the droplet is bigger, then it'll collide faster, so it'll merge to the smaller droplet, and so on. So this droplet eventually merges into a one droplet at the end. Whereas for the Rayleigh plateau instability, you'll see a bead that is space at the constant, and to see a bead dropping down. So we compare our method against the generic finite difference method called GM and BM. All of these are defined in the paper more in detail if you're curious about it. So for generic finite difference method, you'll see that indicated by the blue square, the solution will have negativity. And this is a false numerical negativity, because once you refine the generic finite difference scheme at a very, very, very fine mesh, you will not see this happening. So, and our bonded entropy method, on the other hand, does not show any of the negativity at any moment, and it is very likely for when the droplet to merge to develop negativity, because that's where the solution drops down, and then it's very prone to have a inaccurate solution. But our method didn't show that either. So this is a close-up of the previous simulation. So if you take a snapshot of coarse GM simulation, so this was generic method, coarse BM, this was our method, and fine GM simulation, you'll see that our numerical method actually matches the fine GM simulation better in the sense of the L2 error, and you can also see the profile. The height, for example, matches the our method matches the fine GM simulation better, which is a reference solution. Comparison between laboratory experimental data. So we did the Rayleigh-Plateau regime and isolated droplet regime. Rayleigh-Plateau regime match well, despite the fact that both BM and GM slightly overpredict the speed, beat traveling speed. And we suspect that this is because of sleep effect, because we didn't incorporate sleep effect to one of the simulation. But it even then makes a really good prediction of an actual solution. And then here the experimental data was achieved through the image processing. So previously there was a experimental figure. So the way we acquired this was take a snapshot of this and then do the image processing like Otis method, and then the image segmentation method to get the actual data. So this is actually, you know, raw data achieved from the image processing. An isolated droplet regime, you see that it's really harder to match isolated droplet regime because it has a multiple nonlinear, it has multiple bumps, but we still see like there is a reasonable match. And if you see like around this particular point, you see that the experiment goes down and goes right back up, which in our BM does the same thing, but for GM, it predicts the state as a flat, which is actually wrong. So for the same grid resolution, BM is superior at predicting experimental data. One can incorporate adaptive time stepping in order to expedite the simulation. The reasoning is this. In the very beginning, because we're considering slightly perturbed data from a constant state, delta t has to be kept very small, because in the beginning, you have seen from the simulation, for example, the dynamic changes drastically, very fast. But after a while, you see almost constant profile flowing from left to right. So it'll be inefficient for one to use a very small time step. So therefore, we implemented adaptive time step, where in the beginning, the time step for simulation will be taken very small, but over time, the delta t will be increasing. Delta t will be increasing in the following way. Whenever we solve our explicit, implicit, discrete time skip, discrete discrete numerical method using Newton's method. So we increase delta t by 1% whenever Newton's method converges. Whenever LTE, and this stands for dimensionless local truncation error, which is defined as following. Whenever dimensionless local truncation error is less than a certain tolerance, we increase the time step by 20%. That's a lot, but it's still able to handle that. And we increase the delta t by 50% if the Newton's method fail, because we have to try Newton's method with a smaller time step now. So this is like not the interesting case, and then we'll talk about the interesting case in the next slide. In the case when we don't have any singular behavior, BEM is able to increase. In this case, the Newton's iteration actually always succeed, and then delta t is increased by 1% every time. And local truncation error constraint is also met every 3 times. So the delta t is increased by 20%. So 1% increases and then 20% every 3 times. For this one. For the singular behavior cases where the numerical profile becomes like this, where our H becomes extremely small and having multiple unstable regions, we see that our methods are not able to increase 20% every 3rd time. In this case, it will increase the time step very fast in the beginning, and then at some point, it's going to not meet the local truncation error criteria and go up. And what happens after this is that sometimes Newton's method will fail, so the time step will increase in half, and oscillate, but it's still it's still fast. And let me show you what I mean by fast now. So the way we experimented this was that we increased the grid size. First, consider 100 points on 0, 1. Second, consider 200 point on 0, 1. Third, 400 point on 0, 1. Grid point on 0, 1. So that'll give you the following spatial resolution. And we consider GM with fixed time stepping, BM with fixed time stepping, and BM with adaptive time stepping. Fixed time stepping isn't just you just don't do anything about time stepping, basically. GM is not able to work with the adaptive time stepping. I mean, it can, but it'll be actually worse because the numerical system is quite stiff that whenever you try to increase your delta t more, it'll decrease. So it'll be actually not as efficient to do this. So in the case when we consider GM at the fixed time stepping, it fails to preserve positivity at t equals to 0.299. And this is the unitless time. And until this point, CPU time takes following seconds. And you'll see the BM takes slightly longer time for the same grid size and fixed. And then adaptive time stepping, like it's not really improving as much for here either. But either way, BM does preserve positivity throughout the cases. But this you can notice the importance of adaptive time stepping as you increase the grid size. For example, for the last column, you have 400 grid points on 0, 1. First one, fixed GM, second one, fixed BM, and third one, adaptive BM. Fixed GM, it takes 2 seconds until t equals to 3.4765. And it fails to preserve positivity. So it's not good. But our BM is able to preserve positivity, and see this is almost quarter of the time spent, more than a quarter of the time spent, and then we actually simulated until the later time. So efficient implementation of BEM is possible through adaptive time stepping. That's all I wanted to say. So conclusion, so our contribution was to create a positivity preserving finite difference method for the problem of fiber coding. And we provide a general guideline for positivity preserving method for more thin film equation with cylindrical geometry. So this is able to incorporate nonlinearity from cylinder and is able to handle the advection, nonlinearity from the advection. So we hope that this technique will be used to other type of a cylinder. So that's where our future research direction comes. In the future, we want to investigate the convergence of numerical method. That's very important. But convergence of numerical method analysis is very hard for nonlinear PDE equations. And then PDE solution. And we consider the physical properties preserving, structure preserving numerical methods such as mass, momentum, and energy. And we also want to investigate regularity and energy estimate on the continuous solution. We also are thinking about extending our numerical method to 2D without assuming axis symmetry, because axis symmetry version is not bad, but it actually happens to be that depending on the certain fiber diameter and certain surface tension regime, the fiber coating dynamic is actually not axis symmetric anymore. So therefore, that could be an interesting case to consider. Numerical methods for thin film with complex geometry, for example, sphere and ellipsis, those are another thing that I'm considering. Future research for other problem, just wanted to let you know what I'm working on. I'm working on numerical method of elliptic functions on doubly periodic domain with Braxton Osting at University of Utah. Numerical method for thin film equation with Thomas Witelski at Duke University. And numerical method for Fokker-Planck type equation with Yekaterina Epstein at University of Utah. So that's another type of project that I'm working on. Here are the references, and thank you so much for listening to my talk today.
That was great.
Yep.
Does anyone have any questions? I can ask one. I know the thin films one you had referenced on the previous slide, like this other project you might be working on with somebody at Duke. There's this paper I read a while ago. It came out of Andrea's group. I can't remember if Hongji was on it or not, but it was like compressive shocks and tears of wine. Are you working on similar problems to that?
Yeah, could be.
And do the same numerical methods apply?